You think you know how to multiply? Well, think again. Hey there, and welcome to How'd You Get That, where we solve all your math and physics problems. Today we are continuing our discussion on vectors, but this time we are taking a look at vector multiplication, which, as you might guess, is a whole lot different than scalar multiplication. Because of the added complexity that vectors bring to the table, we now have two ways of multiplying vectors together. There is the dot product, also known as the scalar or inner product, and then there is the cross product, also known as the vector product. The cross product deserves its own video, so we're going to be tackling that at a later time. But today we're going to focus on the dot product or the scalar product, which, as its second name suggests, combines two vectors together to create a scalar. Oh yeah, that makes sense. Put two arrows together and we get a non-arrow. Now there's a mathematical justification for how the dot product works using matrices and things like that, but the remarkable thing about the dot product is that it actually, in the physics world, takes two vector properties and combines them into a scalar property. So let's take a look at, for example, work. Work is the measure of energy transfer in a system, and it can be defined mathematically as work is equal to F, the force being applied, dotted with S, which is the displacement that work is being applied across. So F dot S is equal to work. Work is a decidedly non-directioned quantity, it's just a number. So we're taking two vector quantities, combining them and making them into a scalar quantity. In this equation, the dot product is represented by that dot between the two vectors F and S. As you might imagine, there are two different and equivalent ways of expressing the dot product. One using angles and magnitude, and one using unit vectors. Expressed using magnitudes and angles, we can see that the dot product is defined this way. F dot S is equal to the magnitude of F times the magnitude of S times the cosine of theta, which is the angle between those two vectors. Now, generally for the first part of the dot product, finding the magnitude is pretty straightforward. We're going to use the Pythagorean theorem 9 times out of 10. Now, finding the angle between the two vectors can be a little bit more tricky, but often that's given to you in the problem, or it's something that's controlled within an experiment, or it could be found using some pretty straightforward geometry. Now, as you can see in this definition of the dot product, the left side of the equation is completely made up of vectors, and the right side of the equation is completely made up of scalars. I'm using the cosine of theta in the dot product of these two vectors. So, if theta happened to be 90 degrees, I would find that the cosine goes to 0, which makes the whole dot product 0. So if I have two vectors that are perpendicular to each other, their dot product is just 0. Now let's take a look at the second way of defining the dot product using unit vectors. Now I'm going to define my two vectors in terms of unit vectors. So, for instance, vector F is equal to Fx I hat plus Fy j hat. Likewise, S is equal to Sx I hat plus Sy j hat. The dot product is F dot S is equal to Fx times Sx plus Fy times Sy. As you can see, we're just multiplying the like terms together and then adding all of those terms up. This just results in a number. So for instance, if my vector F is equal to 3i hat plus 4j hat, and my vector S is equal to 12i hat plus 0j hat, the dot product looks like this. F dot S is equal to 3 times 12 plus 4 times 0. Adding that together, it just equals 36. Now let's verify this result by using the magnitude angle method. Now I'm going to draw my vectors like this. As you can see, I've drawn them tail to tail instead of tail to head, as in vector addition, because in order to find the angle between the two vectors, I have to draw them like this. Now, how do I find that angle between the two vectors? Well, I can find the angle that F makes with the x-axis, and I can find the angle that S makes with the x-axis. And subtracting those angles from each other, I find the angle between the two vectors. Now this one is pretty straightforward. My vector S only lies along the x-axis, and therefore the angle between them is simply the angle between F and the x-axis. Using some right triangle trigonometry, I'm going to find that the tangent of theta is equal to 4/3. And now I actually don't really need to find what the angle explicitly is. As long as I have the tangent of the angle, I can find the cosine of that angle. How's that? Well, let's draw out this triangle. I know this is a 3, 4, 5 right triangle. 5 forms the hypotenuse of the triangle. So if the tangent of theta here is equal to 4/3, I can see that the cosine of theta is simply 3/5. So I actually don't need to find theta explicitly. All I need to do is find the cosine of theta for my dot product function. And so the cosine of theta is equal to 3/5. Quickly finding the magnitude of the two vectors, we find that F has a magnitude of the square root of 3 squared plus 4 squared, which is equal to 5. And S has a magnitude of the square root of 12 squared plus 0 squared, which is just equal to 12. So multiplying all that together, I get 5 times 12 times the cosine of theta, which is, as we found, 3/5. So 5 times 12, 60 times 3/5 is just 36. It's the same answer. Okay, last thing. We're going to talk about some properties of the dot product that makes it similar and a little bit different than regular multiplication. So first of all, the dot product is commutative. I can order my vectors in any way, so f dot s is equal to s dot f. 2, the dot product is distributive. So f dot vector s plus vector d is equal to f dot s plus f dot d. 3, if there are scalars in the dot product, they can be multiplied in any order. So a times f dotted with s is equal to f dotted with a times s, where a is a scalar. 4, the dot product is not associative. We can see this because if I have multiple dot products in a row, I start to dot scalars with vectors, which doesn't make sense given what the dot product is. So if I have quantity f dot s then dotted with d, that doesn't have an answer because f dot s is a scalar, and that scalar dotted with d doesn't have a real meaning. 5, the dot product does not guarantee cancellation. So even though f dot s may equal f dot d, that does not mean that s is equal to d. We can see this because we can imagine a situation where f dot s is equal to 0 because those two vectors are perpendicular to each other, say. And then imagine a situation where f dot d is also equal to 0 because those two vectors are perpendicular to each other. But then if we compare s and d, we can imagine a situation where s and d are not equal to each other and yet still perpendicular to f. So s and d are not necessarily equal even though they're dot products with f are. So there you have it, the simple and elegant dot product. If you have any questions, leave them in the comments below. And if you have any suggestions on what you would like to see in future videos, leave them there too. Hit that like button and subscribe for more math and physics content. Make sure to hit that notification bell, and I'll see you in the next problem.